Thank you so much. It's an honor to be still a young researcher for both of us, I think. And today we will present you probably a short portion of our recently started project at TU Darmstadt in the collaboration between two departments, mechanical engineering and digital design unit. And I think that watching out the background, introducing DDU is, I think, not simple because we know already in this room, but over the last years and during the PhD, I have spent a time at digital design units led by Professor Oliver Tessmann on the hollow constructions and additive methods, which are not directly 3D printing, but actually adding the layers inside the formworks. As you can see, for instance, this robot rotating and distributing the material inside a formwork, or our small research portion on filling the composites between the 3D printed formworks and field material.
Okay, and I'm the one who's new here with our institute, the Institute of Printing Science and Technology. I think it's the first time for the institute and for me as well to present here with architects and from people from the construction industry. So yes, as Samim said, we are from the Department of Mechanical Engineering, and it was usually founded by 7 printing machinery manufacturers, so let's say ink on paper. And these days we are quite large with 5 different research groups and a very diverse team. So we do from embossing in paper to microstructures and 3D printing with living cells or printed electronics, even cultivated meat, quite a diverse range of 2D and 3D printing. And I'm the group leader for the industrial printing, so I focus on everything with conventional printing and 3D printing with plastics.
Yeah, to the problem statement, I think that the material consumption, plastic generally and globally, is increasing, which is obvious for all of us in this room. And now we are consuming 4 times more than 60, 70 years ago. In the future, we would constantly using more plastics. And if you're taking a look at our industry, the building industry and construction, our consumption is also increasing over the last 20 years. Our consumption increased by 5%. Which is quite a high. And I think shortly reported from our industry, as we have heard today, we are pretty lazy and our productivity is not as much as in the rate of the comparison between the other industries. However, the automation sounds to be a promising, which 3D printing is part of this world. And we have also different difficulties by the plastic, which my partner would explain.
And as 3D printing seems like a holy grail to increase productivity, however, it's slow, it's expensive, and there seems to be a lack of innovation in the process itself. And when it comes to large components, there are new difficulties, especially when we're talking about plastics. So the material cost is high, the speed is low, and we need to cool down the plastic parts, and the cooling is usually poor. So our solution is to 3D print with hollow strands. And on the left side, you can see the conventional 3D printing, where you extrude a solid cross-section of polymer on a build plate. And our approach is to extrude a hollow cross-section, a hollow strand, and we want to expand it using internal pressure. And by inflation with air, we want to create a variable extrusion diameter. So our approach is a highly scalable process with a high volumetric throughput, and we save material by substituting plastic with air, and we have a fast tooling rate as it has thin walls. And this approach of blow extrusion can be solved in 2 different ways. There are 2 routes dependent on the feedstock we use. Many from plastics 3D printing know filament-based printing or fused filament fabrication, and we expanded it to fused filament fabrication blow extrusion. And because we use filament as a feedstock, it's easy to process, it's easy to convey, and we can build small, lightweight printheads. So it's interesting for robotic fabrication. And by using different materials, different filaments at once, we can print multi-material parts. However, for the large scale needed here in this in this scope, we can also use fused granular fabrication, blow extrusion again. And by using pellets as a feedstock, the material is inexpensive and we can have a high material throughput and use the large scale that's necessary for the building construction industry. So we developed 2 different printheads and each were integrated in a fabrication system. So first of all, we made a fused filament fabrication printhead with 4 extruder motors, and the core of the idea is a printhead assembly. And I will go deeper in here. So it consists of several parts. Some are just bought, some are custom made. And it mainly consists of a core where 4 different filaments are fed inside, heated up, and extruded through a nozzle. And there is a core inside that leads to the air. I can show you the air goes just straight through, and the filament is fed through the heat sinks and into the block, heated up, and extruded out. And then we get like a tube. So how does it look like in our 3D printing setup? So first of all, we tried to keep it easy with the one material and try to print a constant diameter. So we're extruding here a hollow structure inflated with some air. And then this seemed to work, so we tried to make it a little bit more complex and 2D printed, actually, it's not 3D printing, with one material and a variable diameter. So, and as you can see, this seems to work as well. So we tried to make it even more complex and go to 3D. And what you can see here is just a sample part. I have it small here, and the larger part is at the beam booth downstairs. And we 3D printed a part approximately 30 centimeters in height with a constant diameter, and then we changed it and changed the diameter. So it's hard to see here, so we made a cut. And on the left side, you can see the constant cross-section, and on the right side, the changing cross-section. And it goes, for example, from 8 millimeter up to 40 millimeters in back. And of course, we did some measurements to verify what we did. And you can see on the gray line is the airflow that we requested. And this results in a size of the extruder. And this results in the layer height. And this is the white line. And the white dashed line is what we actually measured. So we are quite close to what we wanted to achieve. So this works with one material, but we raised the complexity even more and tried to print with a couple of materials. Now it's 4 filaments in CMYK colors with a constant diameter and again with a changing diameter. And I think, again, you can see the constant versus the variable cross-section here. And once again, as you can see on the measurements we did, we are quite close to what we wanted to achieve. And the effect is quite mesmerizing when you look at it in a video. So now that the process seems to work, we wanted to implement it into a robotic setup.
Yes, another setup that we have used is specified for the pellets printing, which is also consists of the conventional pellet printing setup with the modified headsets that we have presented within the filament approach. Again, there is air pressure coming in, air goes out throughout the nozzle, and the material can stay out as a hollow tube around it, which is all built because of these elements embedded inside the conventional parts. And again, back to the digital transition and digital workflow, we have started to making a digital workflow, which is built from different parts and components from our slicers, and then tools that we can allows us that we are varying the airflow during the printing as well as the other fabrication. And importantly, we started working on the same digital workflow that allows us to change any of these extruder parts and giving us the resilience regardless of our machine and the extrusion and the airflow machines as the extension actuators to our robotic setup. We started the challenge of scaling up within 2 directions of vertical printing and horizontal printing, and target to going to reach the limits of the scalability with the hollow strands, which are like inflating and totally different as the procedures that we know by pressing down the material in the layers over each other. within this video and the 6 times more, we started to demonstrating the capacity of the material with the different strands, with the different dimensions. As you can see at this video, we can incrementally changing diameter by manipulating the airflow, or within this video, which I think is very, very more promising on the potentials. We can start with the 20 milliliter per minute, the airflow, starting to increasing the air pressure and the feed ratio, and reaching the different varied interpolated sections of the material. And again, starting to challenge, going through the challenge of watching out how can we take a full control over the parameters of the printing to involve the material flow and the air pressure into our system, to controlling them, and finally getting something that makes us happy and promising that we can transit the digital to the physical workflows, which is in this case not, but it's a very beautiful picture. And in the next prototype series, we are getting closer and closer and closer to our aiming. And I think one very important fact of this interdisciplinary work is that extracting the data during the work and during the procedure allows us to making the feedback loops to see what are exactly the stand of the techniques and how can we implementing those measurements and survey of our prototypes, let's say. But the question is, what can we do with 5 kilograms of the PETG? We can build a cube 15 by 15 by 15, quite packed. We can 3D print it with the 10 millimeters of what we all know, the solid materials. We can go for hollow strands, making it longer, or we can go for hollow strands with variable layer thicknesses. And in our demonstrators, as Philipp mentioned, that are here in the exhibition, we have demonstrated that we can scale this system up, which is built in the 2 pieces regard of our working hours and capacity of the robotic reach. And we are looking forward for more implementation of the different functionalities in the industry, and to bringing these hollow tubes as a capacity for function integration. Another very important outlook, I think, is here. Which,
the outlook is not me, it's the video. But yeah, we can also print with elastic materials and to create flexible or inflatable parts. So somewhere has one here you can touch and squish it if you want to. And now we come to an end of our talk, and thanks to the team and everybody involved. Thanks to Nastasia, she's sitting here. And thanks to TU Darmstadt for the funding, and to our students who did a lot of work and put a lot of effort into this project. Thank you.
Thank you very much. We have time for a couple questions from the audience. Could you please raise your hand? Yep.
Hello, hi. One for you, it depends. My first one is, I'd like to know, will you share in the future, make public the workflow and using Rhino? The way you actually modulate the air and everything? When you produce, I imagine it's a G code that you made to do that? Or it will be, do you intend to share this in the future? And okay.
Yes, definitely. I think it's a very good question. May I ask you the first question? And then you go for the next one?
Yes, perfect. Yeah.
I think it's very relevant. I mean, we're both from the academic background, and sharing is like the mission of us in the academic world, I think. But I think this workflow is very interesting to publish. If someone is interested, definitely. They're like all based in Grasshopper and Rhino components. And we are now adding more and more the layers of the complexity, because all these different parameters are the variables that need to be somehow jigsaw to each other. But definitely publishing the script is, I like it at least. But if it's in the stage that is possible, I mean, it's ready to publish, definitely.
I will really love it. Okay. And okay, thank you very much. A second question, will you apply this technology to the glass, product in the future?
Until now, we didn't until now we didn't think about it, but may be an option because it looks like blowing glass. Yeah, so let's see if it's technically feasible. So if you want to fund us, maybe.
How much money?
So we re-invite you in a couple of years to see the glass print. We have time for one more question from the audience. Yep.
I asked so many questions today.
You will have time in the breaks. I'm sorry you are a little bit time bound, but you will have time in the breaks for speakers.
In the examples we've seen so far, you've had a single extrusion. Have you bumped up against any limits regarding the pressurized volume as the pieces get larger? And do you have strategies for sealing off one extrusion volume and starting up another pressurized volume?
Yeah, that's critical. Actually, when we start a print, we just print a line, then we seal it somehow with a screwdriver or something, just put it down, then it's sealed, and then we can start our print. And of course, when we scale it up by inflating even more, there's this one moment when we touch our nozzle, and then it ruptures, and the air goes out, and the print fails. So yeah, that's crucial. And there are some ideas how to seal it for a next print. Like, sounds a little bit awkward, but you can seal it like with the robot, like with a sausage. So you can twist it around and then it's sealed, but we didn't try it yet. So it's a work in progress.
I have to mention, this is 6 months of development. It's like half a year project. It's like very baby project.
Thank you.